often the metric space that we are considering will not be connected. But the assumption of connectedness might simplify our study. Thankfully, if a space is not connected, it always breaks up into pieces that are connected, and in such situations we can deal with each piece separately to simplify our analysis. So let's define what these connected components and path connected components are, which are supposed to be the pieces. Definition: let X be a metric space. Let X be a metric space. Define an equivalence relation X on X with X being related to Y if and only if there exists a connected, respectively path connected. So this is going to be a dual definition. Both the definition of a connected component as well as a path connected component will be built into this definition. If and only if there exists a connected, respectively path connected set Cx, or let's just say C, no need to complicate the notation any further, connected set C subset of X such that X comma Y are both in C. Okay, so what this says is two points are related if you can find a set C that contains both the points, and C is connected. That's for the definition of connected component, and C is path connected for the definition of path connected component. Okay, now the fact that this is an equivalence relation is a very easy exercise. You have already shown that the union of connected or path connected sets that contain a particular point in common is always going to be connected, respectively path connected. Using that, you can show that this is an equivalence relation quite easily. So the connected, respectively path connected components of X are nothing but the equivalence classes under this relation. So the space breaks up into various pieces, and it will turn out that each pair of points that is there in a given connected component, a given path connected component, can be connected by a path, and each connected component itself is going to be connected. Okay, let's prove this fact, because that's what this definition is actually modeled on. This entire definition is to make sure this proposition is true. So let's just first prove this proposition. The connected path connected components are connected path connected. So the whole definition was to ensure that this is true. Okay, now the proof is very easy. So I will just consider the case of the connected components. Proof: let C be a connected component, of X that contains X, a given point. Then if Y is in C, there exists some Cx, or rather Cy, such that Cy is a subset of X and Cy is connected. Okay, of course there exists Cy such that Cy is subset of X and Cy is connected, and of course I must mention x comma y are both in cy. So given any point x in x, we can, and a point y in C, where C is the connected component that contains x, then we can always find a connected set Cy that contains both x and y. Now it is obvious that in fact Cy is a subset of C. This just follows because of the very definition of the equivalence relation. In other words, C is nothing but the union of all Cy as y runs through C. Okay, and all these Cy's contain the point x. That's how Cy was defined. But a union of connected sets that contain a point in common is connected. Therefore, C is connected. Therefore, C is connected. Since you can express the connected component that contains x as a union of connected sets, all of which contain x, the union is going to be connected. Okay. So this proposition prompts the following remark: the connected component that contains x is in some sense the largest connected subset of x that contains x. So it's a piece. It's one of the pieces of x, and it's the largest piece that contains the given point x. Okay. Now I'm just going to prove a couple of basic facts about connected components. These connected components will become more important in a course on topology or manifolds or some such. So deeper properties you will probably learn. There's not much more to this notion. So first is, a connected component is always closed. Connected component is always closed. And the proof of this is just one line. Proof is, if C subset of x is a connected component, then C closure is also connected. Right? So given the fact that C is a connected component, that means that if you take any point x in C, and if there is a point y such that x and y belong to the same connected set, then that entire connected set should belong to C. So applying this argument to C closure, which is connected, immediately shows that C closure must be a subset of C, which means C is closed. So this in some sense is following because connected components are in some sense definitionally the largest connected pieces of the set X, and C closure is a larger connected piece. Okay, so here is another remark needs to be made. This is not true. This proposition this is not true for path connected components. So please come up with a counter example to see why this is not true for path connected components. In fact, we have already seen a counter example. It's more like you have to figure out which is the counter example. So let me end this short video on connected components with this proposition. Connected components of an open set U in Rn is open. Okay, proof, and again the proof is rather easy. Let C be a connected component. Suppose X is in C. Then by openness we can find BXR subset of U open, right? Open ball, and BXR is connected. I want you to think about why BXR is connected. We have actually shown it already. BXR is connected, so BXR must be contained in C, showing C is open. Showing C is open. Now let's end this section on connectedness with the remark. You might wonder, why is this not true for an arbitrary metric space? I mean, after all we have used is the fact that given any open set and given a point, we can find a ball. Well, the reason is BXR need not be connected in an arbitrary metric space. It's connected in Rn because it's actually convex. So I'm going to spoil the surprise for you. It's actually connected because it's convex. This is not in general. The notion of convexity itself doesn't make sense in any arbitrary metric space. Furthermore, you can construct examples of metric spaces where BXR is not going to be connected. This is a course on real analysis, and you have just watched the video on connected components.